right, we're now continuing into reading about yesterday's lab, bending light. So we're looking at how light interacts with different mediums. Have you ever tried to pick up something from the bottom of a container of water and the object was deeper than you thought it was? This happens because when light waves are transmitted, they can change direction. Light always travels through empty space at the same speed. The speed of light is always the same, and that is 300,000 kilometers per second. Light travels more slowly through a medium such as air, glass, or water. The particles of the material interact with the light waves and slow them down. Some substances, such as air, only slow light a little or small amount. Others, such as glass, slow the light more. You can see in this picture over here, we have a piece of a rectangular glass prism, and it's shining a light through it. The light is going here, but then when it hits the glass, it bends, and then it continues as it comes out of the glass into air again. So this is called refraction of light. Because the speed of light changes as it transmits, there's one of our old vocabulary words, transmits from one medium to another, the direction of light will change. If light enters the new medium at an angle, then the wave will change direction. So notice like this light wave up here is coming in at an angle. It's not straight on, it's coming in at an angle. The change in direction of a wave as it changes speed while moving from one medium to another is called refraction. And there's a new vocabulary term, and we're going to add this to our foldable. If you've forgotten, here is our foldable. I'm going to show you how we're going to add that in a little bit later. For example, when you visited an aquarium, and here's a picture of the Monterey Bay Aquarium, the aquarium closest to where we live would probably be the Long Beach Aquarium if you've ever visited there. The light bounces off the fish and then to your eye. However, when the light is transmitted from water to the air, it changes direction. You will always see the fish further away than the fish actually is. This means, unless the fish is out of water, you can only see a virtual image of the fish. So what you're seeing here is actually a virtual image. It's not the real fish. It's not the actual place in which that fish really is. It's a virtual image. Moving on to the Index of Refraction. This is on the bottom of page 112. Each transparent material has a property called the Index of Refraction. Now, as shown in this table right here, a medium that has a high index of refraction is sometimes called slow because light moves slowly through it. A medium that has a relatively low index of refraction, such as air, is called fast. I know this is kind of confusing. When light is transmitted between two materials, the amount light refracts depends on the difference between the indices of refraction of the two objects. Now, if the index of refraction is the same, then the light will not refract. Meaning, if it has the same index, if it's the same number, then it will not bend. It'll go in a straight line. It'll appear to go in a straight line. It will not refract. It won't bend if the index is the same. So here's a really cool chart right here. Here's some different materials or mediums, and here's their index of refraction. Notice in a vacuum, it has an index of 1. 1, that is the speed of light. It cannot go any faster than that. That is the speed of light. But as it hits other things such as air, water, or glass, you can see the index of refraction begins to get higher and higher and higher, and the speed gets slower and slower and slower in kilometers per second. Okay? That can be kind of confusing. So we've got the higher the index, the slower the speed. Okay, the higher the index, the slower the speed. Okay? All right, and now speaking of slow and fast, over here we're going to talk about different mediums. So suppose, here's a way of thinking about how or why light is bending the way it is. Suppose you roll a toy car across a table straight at a piece of fabric. The front tires of the car slow down when they hit the fabric. The car continues to move in a straight line, but just more slowly. Now, if you roll the car at an angle, one of the front tires will hit the fabric before the other, and that side of the car will slow down, but the rest of the car will continue at the same speed until the other tire hits the fabric. This will cause the car to turn and change directions just a little bit. A light wave behaves in a similar way when it moves into a slower medium, shown in this figure right here. Recall that the normal is a line that is perpendicular to the surface. As light moves into a slower medium at an angle, it changes direction toward the normal. Now, faster mediums. What happens when light in the figure moves back into the air? So coming back into the air here. Well, suppose you ride your bike from a sidewalk, then to the muddy field, and then back onto the sidewalk. You use the same amount of energy to pedal the whole time, but you move more slowly in the mud. When you move back onto the sidewalk, you can speed up. Similarly, as light moves into a medium with a lower index of refraction, it speeds up. The wave is still at an angle, so part of that leaves the slower medium first and speeds up sooner. This causes the wave to turn away from the normal. So here we have a picture showing it going from air through glass and then back to air. So we see as it hits a slower medium, the glass, then it will bend toward the normal, imagine this perpendicular line, okay? And then as soon as that hits another normal perpendicular to the surface line, then it's a faster medium, then it's going to bend away from the normal, okay? Now we're going to add these to our notes. So let me go ahead and pull this away, and I'm going to bring in our foldable. So far we've talked about light and how we talked about electromagnetic radiation. We talked about the electromagnetic waves. We've talked about how light interacts with matter. We talked about transmission, transparent, translucent, and opaque substances, materials. And then we talked about the law of reflection and how light moves in straight lines, and there is a law of reflection, and it will reflect at an angle of incidence. Remember, the normal is perpendicular to the surface. We did talk about concave and convex lenses. We're actually going to come back to that. This is moving through it, and then here's the rough surface. And then now we're going to start with our next flap here. As you see right here, is going to say refraction-bending light. Okay, refraction-bending light. So I want to make sure that you guys remember that light always moves in straight lines. And I put the definition of refraction right here. It's the change in direction of a wave as it changes speed while moving from one medium to another. I just copied straight from the book our Index of Refraction. It's straight off of page 112. And I actually added in the faster and the slower speeds on the side here. So I know that, a lower index of refraction is actually faster than a higher index of refraction. And then over here, I did the same picture that you see on page 113, and I wrote, as light goes through different mediums, here's what it does. And it bends air, glass, air. We've got the normal. We've got it going towards the normal and then away from the normal, and goes slower and faster as it changes there. So that is our foldable. If you want to copy this, I've also put it in the slide deck attached to the Google Classroom assignment. All right, the next thing we're going to be doing is going down to the 3D thinking. So the light from the sun travels through a vacuum. Now remember, vacuum means there's no air, to Earth's atmosphere. Now, unlike sound, light does not need something to go through. That's why light can travel through a vacuum, but sound cannot. So let's make an argument from the evidence that we learned today that the sun actually goes down below the horizon before you even see it set. What? You say? Yes, the sun actually goes down below the horizon before you see it set in the west. So you can use my frame or you can come up with your own sentences, but I framed it as, when light from the sun enters the Earth's atmosphere, what does it do? What do you know that it does as it enters the Earth's atmosphere from being a vacuum where there's no air and then it enters Earth's atmosphere where there is air? What's happening? What does it do? Therefore, the sun's light will do what? What's the light going to do? Which allows its light rays to still be visible even after the sun is actually set. Actually set, it's gone. It's behind, over the horizon, but it looks different to us. We can still see it. Okay, so I'll leave that there for a moment. And the last thing we're going to do is we're going to go back to page 108 and we're going to add this to our evidence of our CER. So this is evidence A of our CER. So I'm going to flip back over to page 108. And here we are at evidence A. What happens when light passes through different mediums? So you can do your own. You can draw pictures if you like, or you can use my frame. When light travels through different mediums, it travels at, tell me this something about speed. Different mediums, what happens to the speed? Now, as it moves from one medium to another, what does light do? When it goes from one medium to another, from air to light, or from air to water to glass or a solid, and then back to air again, what's happening? What does it do? Okay, and then once again, that's on page 108, and that is the end of today's lesson.